All right, so in the previous lecture I told you, or in the previous two lectures I told you a little bit about how to choose the finite element. Now, when you implement the finite element method, you always have the bilinear form on the right-hand side that include integrals. And we know that we cannot compute integrals exactly, that typically we need to do quadrature. And so the question that you would have to answer then is, well, how exactly do we do this quadrature? What is the, let's say, what is the quadrature rule that we want to apply to this? So in this lecture 33.5, I would like to talk about what quadrature formula to use. And let me recall the basic approach that we have to forming the matrix in the right-hand side. This is from lecture 4, and you've seen this in many of the Azure example programs as well. So when we want to compute a term like grad phi I, grad phi j, which is the aij entry of the system matrix, or to compute fi, which is phi I times f, that's the ith entry of the right-hand side vector. Then the way we did this is that we wrote this as an integral, right? This is integral grad phi I, grad phi j. We split the integral over cells. So we have a sum over all of the cells, and on every cell we want to form grad phi I times grad phi j. And then we pulled everything back to the reference cell, k hat. Okay, so for every cell, we pull it back to the reference cell, and then do a coordinate transform from the real coordinates x to the reference coordinates x hat. And so in order to write the gradient of phi I, we wrote this as the inverse of the Jacobian times the reference gradient of the reference shape function on the reference cell. We do this for phi I. We do the same thing for phi j. And then we get the determinant of the Jacobian as a as a weight in there. This is the place where we then apply quadrature. Okay, so we replace the integral here by a sum from little q equals 1 to capital Q, and we evaluate the integrand here at points xq hat defined on the reference cell, and weigh them with quadrature weights wq. And we do the same thing for the right-hand side. Now, this term over here, the determinant of j times w, this is what in deal.II we call jxw, and I always wanted you to think of this as the equivalent of the dx in an integral. So when you have this approximation where this is the exact integral we would like to compute, but we can't, so we replace it by a sum over all of the cells and quadrature on every cell. The question, of course, is how do you choose these points xq hat and the corresponding weights wq, right? In other words, what is the quadrature rule that we want to choose? So when I say quadrature rule, a quadrature rule is shorthand for a set of points xq hat and corresponding weights wq. I must admit I don't know where that term comes from, but quadrature rule is a set of the xq hats and wq's. So how do I choose this? What are the points that I want to choose and the corresponding weights? Now, from a practical perspective, of course, what I would like to do is I would like to make this capital Q here as small as possible, because if this capital Q is 100 here, for example, then that would mean that I need to evaluate this whole integrand 100 times on every cell. That's not what I want to do. I would like to make that as small as possible, so I would like to choose these xq hats and the wq's so that the set is as small as possible. On the other hand, I would like to make the result accurate. So in particular, I don't want to introduce unnecessary errors, right? I need to form an integral. I can only form an approximation. I want that approximation to be as close as possible to the exact value that I need. Now, how accurate do I need to be? Basically, the guiding principle that I need to obey by is that I don't want that the error that I introduce by quadrature dominates the discretization error. So for example, let's say I use a quadratic element for the Laplace equation. Then in the H1 norm, I get h squared for convergence. But that is under the assumption that I have exact integrals. Now, if I approximate my integrals and I only get convergence order of h, then that is too large. That I cannot tolerate in a quadrature error that destroys the convergence order. What I can tolerate is if the error that I get after quadrature is still h squared, but with a larger constant. Okay, so that's sort of the trade-off. I'm willing to make an error by quadrature, that's okay, but I must do it in such a way that it does not destroy the convergence order. So let us try to figure out how I need to do this. So I would like to do this first for the 1D case, because in 1D I can do a lot of things that are easy to understand. So for example, let's say I have an element of polynomial degree k. Okay, so these phi i's of x hat here, they are all polynomials of x hat of degree k. Let's say in 1D I have a domain that is just an interval, and I split that into little subintervals, and every one of these subintervals is mapped from the reference interval. So my x hat is from 0 to 1, and I map that to one of the little elements of my mesh, of my one-dimensional mesh. And I'm going to use a linear mapping that essentially means I'm going to squeeze it linearly and then translate it. Okay? So if I use a linear mapping, I can look at the Jacobian of this mapping. Well, if the mapping is linear, the Jacobian, that's the derivative of the mapping, is a constant. The determinant of the so it's a constant matrix, which in this case is a 1-by-1 matrix. Of course, the determinant of a constant matrix is a constant. The inverse of a constant matrix is also a constant, and the same here. When I say constant, of course, a constant on every cell as a function of x hat. So this term, and this term are all constants. Now, these terms here, these gradients of phi j, if phi j is a polynomial of degree k, then the gradient is a polynomial of degree k minus 1. Okay, so the gradients are a polynomial of degree k minus 1. The whole integrand, in fact, is a polynomial of degree 2k minus 1, because I multiply a polynomial of degree k minus 1 and a polynomial of degree k minus 1. So I get 2k minus 1. We know that the most efficient way of integrating things is Gauss quadrature. So Gauss quadrature with n points is exact for polynomials of degree up to 2n minus 1. So in particular for this case in 1D, if I choose n equals k points, I can integrate this matrix entry here exactly. It's not just an approximation, it's in fact exact in 1D if I choose n equals k points. So for example, if I use linear elements, I would have to choose one quadrature point, which the Gauss formula would choose at the center of the cell. If I use quadratic elements, I need to choose 2 quadrature points per cell. So that's all I need to do. So in 1D, forming the matrix is actually not all that complicated. How about the right-hand side? So if I compute the right-hand side, this is, of course, the integral of phi I times f, and I split this again into cells, and on every cell I do quadrature, so it is evaluating phi I at xq hat times f at xq, that's the real space location of my point xq hat, okay, times the determinant of the Jacobian times wq. This here is a polynomial of degree k. This here, in general, of course, is no polynomial at all, right? So my f may be whatever it is. Somebody gives me an f, I have to integrate it. There's nothing I can say in general about it, whether it's a polynomial or not. So the integrand is not a polynomial. What do I do about this? So for general f of x, I can ask the following question. What happens when I apply quadrature to it? Okay. Now, so there's a typo on this formula that I'm going to fix. What that really means when I apply quadrature to a general f is that that is approximately equal to integrating a perturbed f exactly, right? So I argued that if in the previous case, so if f, for example, would be a low-degree polynomial, then the quadrature would be exact. But f is not a polynomial, so what does it correspond to? Well, it would correspond to integrating exactly a polynomial f tilde that is exactly equal to f at, well, the quadrature points and n minus k other points. So on that formula there are two mistakes. It should be 2n minus k here 2n minus k here, and it should say n minus k down here. So quadrature of an arbitrary function is equivalent to integrating a polynomial of degree 2n minus k exactly. So on this slide, it's actually correct. So it corresponds to integrating exactly I to n minus kf, where this is the interpolation onto a 2n minus k dimensional polynomials on every cell. So the inexact integration, the quadrature, is equivalent to computing the exact integral of an approximate function. And I can ask, well, how exact must this approximation be? And I can quantify that. So if you think about that this is the problem that I want to solve, minus Laplace u equals f, the one where I have on the right-hand side not the original f, but the interpolated polynomial of degree 2n minus k, if I use Gauss quadrature with n points, corresponds to solving a different problem, okay, namely minus Laplace u tilde equals f tilde. So if I look at the error u minus, and well, I can't compute UH because that would involve the exact computation of integrals. All I can compute is UH tilde. That is, UH tilde is the finite element approximation using quadrature. Okay, so I can split this norm here into two pieces, namely u minus u tilde plus u tilde minus UH tilde. Okay. U minus u tilde corresponds to these two solutions of the exact problem and of a perturbed problem. And u tilde minus UH tilde corresponds to the solution of a perturbed problem minus the finite element solution of the perturbed problem, which exactly equals the finite element solution using quadrature. So this here, I know what that is. That is an error that is proportional to h to the power of k times the hk norm of u tilde. Right? That's what I always have. Over here, I can ask what is the difference between the solution of this problem, and that's relatively easy. I can subtract the two problems from each other, so I get minus Laplace u minus u tilde equals f minus f tilde, and then I can use elliptic stability, and what I find is that that is proportional to f minus f tilde in the h minus 1 norm, which is proportional to h to the 2n minus k plus 1 times the h 2n minus k norm of f. Okay. So I haven't said anything about how to choose n in the in this particular case. How many quadrature points do I need? Well, I want the first term to not dominate the second term. Okay, so I need that h to the 2n minus k plus 1 is equal to k, and I can achieve that again if n equals k. So again, also for the right-hand side, no matter whether f is a polynomial or not, if I want it to be accurate enough, I need to choose n equals k. So for linear elements, one quadrature point is enough, even if that means that I cannot integrate exactly the right-hand side. All right, so how about higher dimensions? So in higher dimensions, what I have is that these phi i's are polynomials of degree k in each coordinate direction, in each one of the, let's say, x1, x2, x3 directions. And these j's, in the simplest case, correspond to a D linear mapping. Okay, so I'm talking about, let's say, using quadrilaterals and hexahedron. So the whole thing actually becomes pretty messy in that case, because the matrix J is a polynomial of degree k in every variable. The determinant of it is k to the d in every variable. The inverse of this Jacobi matrix is in fact a rational function in every entry. The gradients of these phi j's are polynomials of degree dk minus 1. That's the total degree in that case. So the whole integrand that I have here is not a polynomial anymore. It's in fact a rational function because I have these jk to the minus 1 here. If I happen to have a polynomial, if I happen to have a linear mapping, so for example, if I work on a mesh that consists only of rectangles or parallelograms, then the mapping is linear, and in that case the j's are constant, and the j to the minus 1 are constant. And all of these terms that involve j don't factor into our consideration. I only get certain polynomials out of gradient phi I, gradient phi j here. Okay, and then you can convince yourself that it is a polynomial of degree 2 dk minus 1 of total degree, d being the space dimension as always. So what I get out of this is that the total degree is 2 dk minus 1. We know that with Gauss quadrature, n points in every direction yields exact integration for polynomials of degree 2n minus 1 in each variable. 2n minus 1, that is the polynomial degree in x1, x2, x3, not the total polynomial degree. When I look at this formula, it's not immediately obvious how I need to choose n. And so you can go to great lengths. You can look it up in the book of CRLA, for example, or in Dautrey-Lyon. And what you will find is that you can apply quite sophisticated mathematical analysis to this. And what you will find is that in order to not destroy the convergence rate of my scheme, I need to use a quadrature formula where n equals k plus 1. So in that case, we know we create errors by replacing the exact integration by quadrature. But the error that I introduce this way is not so large that it destroys my convergence order. So the general rule is that when we do this, that I use Gauss quadrature with n equals k plus 1 points per direction. So for example, if I use bilinear elements, then I need to use a Gauss formula that uses 2 times 2 quadrature points. So 2 in x direction, 2, let's say 2 in x1 and 2 in x2 directions. Similarly, when I use quadratic elements in 3D, I would have to use 3 by 3 by 3 quadrature points. So this leads to, if you go to the deal.II example programs, they almost always use, at least in the higher tutorial programs, they almost always use q Gauss fe dot degree plus 1. Fe dot degree is the polynomial degree in every variable, plus 1 would be n equals k plus 1. So that's sort of the general rule that you want to obey. The same thing can be said for the right-hand side. So for the right-hand side, you run into the same kind of problems. It's not a polynomial, and you need to evaluate what the error is, but you come out at exactly the same kind of result, namely that you need to choose n equals k plus 1, and that's the rule of thumb that you should always obey. So as a general rule, Gauss quadrature with n equals k plus 1 is sufficient for the Laplace matrix. That should, of course, go here. For the mass matrix, you can have the same kind of consideration. You will find that there too, n equals k plus 1 is sufficient, even though the polynomial degree of phi, of course, is 1 higher than gradient phi. Okay? And it's also true for fi. It is also generally true that if you have a Laplace matrix with a coefficient, let's say an a of x in here, that even if this a of x is spatially variable, then n equals k plus 1 is generally still appropriate. So the quadrature error in that case does not dominate the overall error, or at least it does not destroy the convergence order. So there are a few corner cases that you have to take into account. Namely, if you think, for example, that you have a coefficient a of x in your Laplace equation that could be discontinuous, or if you have a discontinuous right-hand side, then you can think about what it is that Gauss quadrature or any other kind of quadrature usually does. Quadrature works the following way. You take your function, you evaluate it at individual points, you find yourself a polynomial that interpolates these points, and then you integrate the polynomial. And we do this because we can write down the antiderivative of a polynomial. We can write down the integral of a polynomial exactly. And so what we do in quadrature is we replace the function by an approximating polynomial, and then we integrate the polynomial. And as long as that function is smooth, we know that if I take more and more interpolation points, then the approximating polynomial becomes closer and closer to the original function, and the integral will become more and more accurate. But that argument breaks down if your function f, or the coefficient that you try to integrate, is not smooth. for example, if it has a kink or if it is discontinuous. So if you take this sort of situation, let me say my coefficient or my f is this red line here, so it is discontinuous, and I'm going to evaluate that at 4 points here and here and here and here. And then I'm going to try to find the polynomial that interpolates that function. Okay, that's the green curve here. And then I'm going to integrate that. And if I ask you the question, well, so is the integral under the green curve a good approximation to the integral under the red curve? Then the answer is almost certainly no. So for cases like this, where this function is discontinuous or at least not smooth, polynomial integration does not actually yield very high accuracy, right? We don't, by taking more and more points, we do not get the error to be smaller. So I can quantify that again. So if I do the same kind of argument as we did for the 1D case, that U is the exact solution, UH tilde is the finite element approximation using quadrature. I split the error into the difference between, well, the exact right-hand side and the polynomial approximation of the right-hand side minus the solution with the polynomial approximation of the right-hand side minus my finite element solution. This term, again, I know what it is. It's h to the k. And before, I had that this thing here converges with the h minus 1 norm of f minus f tilde, which was h to the 2n minus k plus 1. But this step fails now because f minus f tilde, if f is not smooth, then I cannot form the h to n minus k norm of f. Let's say if f is only piecewise constant, or let's say if it is discontinuous, then I can only use the hs norm, for example, the L2 norm. And that whole term here will yield only h to the s plus 1. So this thing here will have a convergence order that is independent of the number of quadrature points. And there's nothing I can do about it because this f is not smooth enough. And what that means is that I cannot choose n in such a way that s plus 1 equals k. That's just not going to work because it's independent of n. Now, you can say, well, okay, then what do I do? So what I do in a case like this is that instead of just using a Gauss formula of higher and higher order, I use a relatively low order Gauss formula, for example, with n equals k in 1D or n equals k plus 1 in higher dimensions. And I'm going to iterate it. So that means that I'm going to apply this polynomial interpolation not on an entire cell, but I'm going to apply polynomial interpolation on this piece of the cell, plus this piece of the cell, plus this piece of the cell, plus this piece of the cell. And then I'm going to add up the integrals under the local approximations everywhere. And you can easily convince yourself that in that case, of course, the error is not h to the s plus 1, but h to the l to the power of s plus 1, where l is the number of subdivisions and h over l is the size of each subdivision. Okay, so what I can do, if I do this, then I end up that this first term here is something like h over l s plus 1, and I want this to be equal to the error over here. Okay, so I just need to make this L large enough so that I can get this error to be on the same order as this one, or of the same size. Of course, one of the things, so yeah, I should say that this is exactly what the Q-iterated class does. It takes a Gauss formula, for example, and applies it on small subintervals. There's one other thing that's worth considering. So if you say I use polynomials of finite elements of degree k, then let's say if I choose k equals 3, I should get cubic convergence order here. And well, what do I do here? If my right-hand side is only piecewise constant, then I can only take s equals 0, so the L2 norm here, and I would get h to the power of 1. Here I get h to the power of 3. So it would seem like I need to make this L larger and larger, the finer and finer my mesh will be. That's not exactly the correct argument, because when you have a piecewise constant right-hand side, your solution is not actually, in fact, in H3. It will only be, for example, in H2 or H1. And so in a case like this, you cannot actually hope that you get very high order out of this here. So I wrote down h to the k, but in reality is actually maybe h to the 1 or h to the 2. And so it is much easier to actually make this term on the left-hand side here converge with the same order as the thing on the right. Okay, so there's two other cases that I would like to consider, namely what we call special purpose quadratures. So we can sometimes apply other quadrature rules other than Gauss to affect either the stability properties of a discretization. So there are cases, for example, where you have nearly incompressible elastic media. In a case like this, what you will find is that you have a similar situation as with Stokes, where the finite element approximation does simply not converge if you don't do the usual thing. And you can either tweak the formulation and introduce a different variable, for example, or you can replace your bilinear form by a bilinear form that comes out of quadrature, where you use a quadrature rule that appears inappropriate for this particular case. Namely, it is a quadrature formula that has too few quadrature points to actually be accurate. It turns out that this relatively stupid trick actually works. So that's one case where you might use something different than Gaussian quadrature. I'm not going to go into much detail there. There are also special purpose quadrature formulas for mixed problems. Let's say for Stokes or for the mixed Laplace, where you have similar cases where you had the inf soup condition and you needed to satisfy that with certain pairings of spaces. There too, you can apply that with, or you can apply a different quadrature rule, and you can get around some cases of the inf soup condition not being satisfied. The other situation, so I'm not going to talk about either of these. The other situation that I would like to talk about briefly at least is where you want to improve the sparsity of matrices, for example, by making some term 0 or making the matrix diagonal altogether. So this is sort of an idea that people use to show the equivalence or a similarity between finite elements and finite differences, for example. Imagine you had a uniform mesh with square cells, and you had Q1 elements. So these are the shape functions of the Q1 elements. And then, of course, I can compute the gradients of these Q1 shape functions, and they look like this. If I took the trapezoidal rule, so the trapezoidal rule places the quadrature points into the corner points of the cells, into the vertices. So they're, for Gauss quadrature, they're in the interior of the cells, but for the trapezoidal rule, they're exclusively in the vertices. Then one of the things that I can figure out when I look at the gradients that I have written down here is that if I put this into my quadrature formula, okay, then it turns out that the gradients, this should have been the grad hat. Well, actually, it doesn't matter. I can work in real space. It turns out that the gradient of phi I times the gradient of phi 3 is 0 at every one of the 4 vertices. Not everywhere in the cell, but at the vertices. And the same is true for the gradients of phi 2 and phi 4. So in other words, shape functions that lie diagonally of each other in a cell do not actually couple. That means that the corresponding matrix entries that correspond to shape functions that are across from each other in a cell are 0. So in a situation like this here, let me say that I have a mesh that looks like this. It turns out that A40 and A42 and A46 and A48, for example, are 0, as are A04, A13, A24, A15, and so on and so forth. So everything that is diagonal here is 0. On the other hand, I can show that A41 and A43 and A45 and A47 are in fact 1/4 of, or minus 1/4 of A44. So in every row of this matrix, you have 4 minus 1s and 1 4. And of course, you've seen that before. That's exactly the 5-point stencil that we get out of the simplest finite difference approximation of the Laplace equation. So if you apply a simple enough quadrature rule to a finite element scheme, you may come out with a finite difference scheme. And in fact, that is one of the reasons why people often say that finite differences in finite elements are the same. I can frequently show that a finite difference scheme converges because I can show that it corresponds to a finite element scheme with a particular choice of finite elements if I apply a particular quadrature rule to it. So if I can show that the finite element scheme with exact integration converges with a particular order, and if I can show that applying the quadrature rule does not destroy the convergence order, then I have just shown that the finite difference scheme converges, right? Because I get the same matrix. So that's one of the ways we have learned how to prove that many of the finite difference schemes that were developed in, let's say, the 1960s, 1970s, actually converge with a particular order. It's often very difficult to show this in the finite different context, because the finite different context only considers the values at particular nodes, whereas the finite element context considers functions, right? And so it's often very difficult to show this for the finite differences. It's much easier to show it for the finite elements if I can show that I get the same matrix out of finite elements and finite differences if I only apply a particular quadrature rule to a finite element scheme. So that is the derivation for the case of the 5-point stencil. If I do this in 3D, I get the 7-point stencil out of it, and that shows, for example, that the 5 and 7-point stencils converge if I can show that the quadrature is appropriate, which it is in this case. Now, one of the advantages that I didn't say here before is that the matrix is, of course, much sparser, right? So if I apply this particular quadrature scheme, every degree of freedom only couples with 4 others around it in itself, so there are only 5 entries per row of this matrix. Whereas if I computed the integrals exactly, degree of freedom 4 would couple with every one of these 9 degrees of freedom here. So it would be 9 entries per row. So I get a matrix that is only half as full as the typical finite element scheme, but it will still converge with the same order because I chose an appropriate quadrature formula here. That's sort of, so like I say, I can do this. I can use the trapezoidal rule. That is not what we typically do. It's more of a theoretical argument that we use in order to validate finite differences. But we still typically use Gaussian quadrature because we can show that the error is smaller, for example. I can extend this a little bit. So if I use the trapezoidal rule for the mass matrix, so the mass matrix is, of course, just the integral of phi I times phi j. If I use the same shape functions again, of course, the shape functions are defined in such a way that they're 1 in one vertex and 0 in all of the other vertices. So if I only evaluate in the vertices for my quadrature, then it's quite obvious, of course, that this matrix must be diagonal, because the matrix entry M12, for example, would evaluate the integral, or would evaluate the product phi 1, phi 2 in all of the vertices of my mesh. But in all of the vertices of my mesh, either phi 1 is 0 or phi 2 is 0. So the product is always 0. So I get a matrix that is, in fact, diagonal. And I can generalize this for arbitrary elements if I choose quadrature points and appropriately chosen quadrature weights, of course, in such a way that the quadrature points only lie at those points where I define my shape functions. So let's say in a Q2 element, I would choose the 4 vertices, the 4 midpoints of a quadrilateral, and the center of a quadrilateral if I'm in 2D. So I would use a quadrature formula with 9 points and appropriately chosen quadrature weights, and then I get a mass matrix that is diagonal. Why do I do this? So typically, this is something that we would employ when we have a time-dependent problem. If you go to time-dependent problems, oftentimes in explicit schemes, you would have to invert the mass matrix in every time step. Well, if the mass matrix is diagonal, inverting it is particularly simple, right? I would only have to store the inverses of the diagonal elements and multiply it with my right-hand side, and that's all I need to do. So it's particularly simple to solve explicit time-stepping problems if I have a diagonal mass matrix. And so that would be a typical application of this sort of approach. So I would say with this, I have told you basically everything that you need to know about quadrature. So basically, the general rule is use quadrature with n equals k plus 1 points per coordinate direction, is what it should say here, where k is the highest polynomial degree in your finite element. So, for example, if you have a q2, q1 Stokes element, you would use 3 quadrature points per coordinate direction. So a q Gauss 3 in any space dimension. If you have non-smooth coefficients or right-hand sides, then you will need to think a little bit harder about it. For example, if you would want to use something like an iterated quadrature rule, and basically you only use quadrature rules as in Gaussian if you know why you would want to do this. For example, if your goal is to get a diagonal mass matrix, then you would think about using a different quadrature rule. But other than that, by and large, you would always use Gaussian. All right, that's basically everything you need to know about quadrature.